good question about what's happening in an NMR experiment. Just like bring it back to this basic stuff, right? We've been analyzing NMRs, but we need to remember what actually happens in an NMR, so right? What happens in an NMR? So what happens is you have a big magnet, right? It's usually B naught. Let's just say big magnet. A big magnet has a big magnetic field. And your hydrogens can be in two different states. They can be in the alpha state or the beta state. If they're in the alpha state, they're lined up with the magnetic field. If they're in the beta state, they're opposite the big magnetic field. The big magnetic field gets everybody lined up, either with it or against it. There's no random, right? No one's off going different directions like they normally are, right? In solution, you can think about, right, molecules are moving all the time. You get them in this magnet, and you lock these guys in one of two states. The alpha state with the field, beta state against the field. So you get everybody lined up. So it's kind of like lining up a bunch of milk, or you go to the carnival, and you throw the baseball, and you knock over the bottles. What are they called? Milk jugs sometimes used to do that, right? And we knock these protons down, right? We have them flip states, all right? We hit them with radio waves. So they get hit with radio waves, right? And radio waves are right? They're not very strong electromagnetic radiation, right? They're pretty weak. We get hit radio waves all the time. But there's enough difference, right, just to flip these little protons, knock them down, and then we measure as they come back up, right? That's what we measure. And every type of proton has a different, right, this distance between alpha and the beta states is different for every different type of proton. Right? So that's why every different type of proton gives its own peak. Right? So right, proton A has a gap of energy here, say 10 of whatever. Proton B can have an energy gap of 20. But they're different, right? Every different proton has a different distance between alpha and beta states. And then remember, as we get the magnet gets better, right, we get that HD, right, we can see the differences between the alpha and the beta get greater. And so we can see that fine differences between the protons, right? Because some protons are very similar. You need the big magnet to see those small differences. So that's how it works.
It has like a characteristic difference.
It absolutely has a characteristic frequency, right? There's a certain radio wave frequency that makes A knock down. There's another radio frequency that knocks down B. Now those differences are very small, right? But the bigger the magnet, we can see those fine differences. Yep.
What do you mean when you say they knock down?
What I mean, so I like to think of it as, right, really they're flipping states and there's some physics-y kind of stuff going on, but I like to think of it as, right, everybody, you're lined up and the radio wave punches you, knocks you down 90 degrees. And you slowly eventually come back into the magnetic field. And as it's coming back in, we measure how it was affected. That's what we measure. Right? It's just like IR, right? In IR, right, you hit a molecule with an infrared wave and it shakes the molecule. We measure how it shakes, right? All these spectroscopies, we're doing something to it and then measuring how it affected it. Whether it's with infrared light, radio waves like NMR, right? We do UV vis light and just measure how it affects it. So we use different types of radiation to do that. So when I say knock down, I just mean you knock it down, and then you just a way of measuring as it comes back into the big magnetic field. That's all you're doing. Oxygen is not included. Right, so oxygen is not included in this. So it's 2 times the number of carbons, 10, plus 2, 12, minus plus n, 13, minus x, there's no x's, minus the number of halogens, halogen is 7, 13 minus 7 is 6, good. 6 divided by 2, 3. I might let you use your calculators.
sapling?
It's 21. I gotta say that. Let's see. No, this is someone's sapling number 21, but I think everybody has almost different problems. But degrees on saturation, we got 3, which of course means 3 pi bonds, some combination of pi bonds and rings. Good. It also says here it gives a positive hydroxamate test, which you don't need to know because it tells you it indicates the presence of either an acid chloride or an ester, right? And you guys don't know what an acid chloride is yet, so I probably picked this because it's an ester then, right? So we can draw an ester piece. We draw the squiggly lines and we don't know what it's bonded to, but we know there's an ester. And that covers at least 1 degree on saturation too, right? That pi bond. So it tells me right here that it gives this positive hydroxamate test.
Don't we just have 1 oxygen?
Whoops. O2. Right. Gotta write the molecular formula right, just like you gotta do the degrees on saturation, right? That'll help. Right, so we know there's an ester, so let's subtract this piece out from our molecular formula. Right, we know we have a CO2 piece, so let's subtract CO2 out. So we end up with C4H7N, right? So we only got 1 piece there. So now let's look at what the IR says. What does the IR have for us? The IR says there's a peak at 2237. There's a peak at 1733. Well, that should be our ester peak, so that makes sense. And there's a peak at 1200. Right, so 12, I mean, you're kind of dipping down into the fingerprint region, right? That's a little tough to see sometimes. It's really useful, the fingerprint region is really useful for the alkenes, right? There's a whole table I gave you guys with alkenes, the terminal ones, the disubstituted, the trans, and the specific IR stretches for those, so that could be helpful. We talk about coupling constants for the alkenes. I'm digressing a little bit here. What is 2237? What does that tell us? What kind of peak or what kind of region is that for in the IR spectrum? What could be going on there? What kind? We could either say it's the triple bond region, right? So it could either be C triple bond C, right? That could be possible, or C triple bond N. That could also be possible, right? We don't know for sure which one, right? But both of them are possible. C triple bond C, C triple bond N. Both are possible, right? So if I'm not sure yet, I'm not gonna subtract that from my total just yet. All right, so I'm not absolutely positive. But again, see how we're writing things down, right? Writing down possibilities, right? So you can even write in the or. I'm not sure. Put a question mark here, right? I gotta come back to that later. I'm not sure. This told me, right, in particular at 1740s, 1733, that that's an ester, plus that they give us that little bit of information, essentially telling us it's an ester. So this is all I know so far. I know we have 3 degrees on saturation. I got 1 covered with the ester. And it looks like I get the other 2 covered with either the alkyne, the C triple bond C, or the nitrile, the C triple bonded to N. I'm just not sure which one yet, right? So I'm not going to subtract anything just yet. So now let's look at the NMR. So what
One more IR.
there's one at 1200, but so what do we think 1200 could be? Look at your tables. Carbon oxygen stretch, right? Well, that makes sense, right? That would be a CO stretch because, right, the ester, right, that gives us an idea also that's an ester, a CO single bond stretch. Right? Ester has a single bond stretch. So another just tells us an ester is probably involved.
Is that 1,733?
Yep, this is 1733. And this is 2237. Two, making it worse. All right, let's look at the NMR. So the H NMR, let's say there's a peak at 1.33 that is worth 3 H's. That's a triplet, you just put a T. And the J is equal to 7 hertz. And that's that coupling constant. That tells us what H's are talking to what other H's. We also have a peak at 2 point, nope, take that back. Oh, shoot. Point at, it's not 2, it's 3.45. Worth 2 H's. And this is a singlet. So no nearest neighbors. There's another peak at 4.27. That is worth 2 H's. That's a Q for quartet. And the J here is equal to 7 hertz. Alright, so how many types of H's do we have? How many types? We have, right, so we write 3 types. Let's label this one A, B, and C, right? I like to label them. So what do we know? Just looking at this quickly, what do we know? What do the coupling constants tell us? The coupling constants tell us what? So that's the splitting. That's the splitting, but the actual coupling constant, so that J value, what does that tell us? So it tells us who's talking to who, who's splitting who, right? So there's actually, right, so don't confuse the two, right? So the J value is telling us these two H's are near each other and they're splitting each other this way. Right? The coupling, right, how that's telling you how they're coupled together. Right? So they're affecting each other and they have to affect each other the same way. So if you're affecting me 7 hertz, I'm affecting you 7 hertz. Right? We're splitting you that same way. If it's singlet, then there's no coupling. There's no nearest neighbors. There's no coupling. Right? So we know A and C are next to each other, right? Just flat out. We know they're next to each other. And A is worth 3 H's. So let's draw a piece. Right? That's worth 3 H's. Right? We'll call these. Right? We'll call these A. And we know A has to be next to what? C. And C is how many H's? 2. So we know that these are C. Now we don't know what C is next to, do we? But we know, what we do know, is C is where? It's down here at 4.26, right? So it's pretty de-shielded. What would you want to put it next to, probably? Oxygen. Okay, so let's just put a note here, right? O, question mark. Now, we got to remember, we've already had this other piece here, and there's an oxygen here waiting for a spot. Right? So maybe this is where this piece goes. It probably makes the most sense. That's actually where it goes. Right? So I would say, let's put this up there to that. So they're now connected. But now let's remember to subtract from our formula. We added 2 carbons. Right? So we're going to say minus C2. And how many H's do we use here? 5. H5. So we have C2, H3, N left over, right? Because right, this oxygen, don't double count this oxygen right here. Right? Don't double count this oxygen. But we had to look at this frequency and realize this is really de-shielded. C must be next to an oxygen. So that covered, we just checked off A and C. Now what about B? Where's B? B is a singlet, where's 3 H's, right? So we're saying CH3. This is B now. And now does B have any nearest neighbors?
Why is there 3 hydrogens? It says 2H.
Yep, that would be wrong. Somebody's paying attention, that's good. Oh, come on. Eraser's not working. So I'm doing this now, right? Can't create hydrogens. If it says 2 hydrogens, let's draw 2 hydrogens, right? Duh. Let's try that again. So now, this is B, right? Now does B have any nearest neighbors? No, so it's not split by anything. So let's subtract out. Well, guys, you should have helped me up here.
Subtract out 2.
Yeah, well, wait a second. I don't do math good, but that's pretty bad. 7 minus 5 is still not 3. 2 would be better?
No, it looks like a 2.
Yeah, pretty sure I said 3. Yep. It's the first time I screw up today. That's not true. Right? So let's subtract out the CH2 that we know, right? We know no neighbors, right? We write no neighbors. So you subtract out CH2. What are we left with? CN. Oh, that could be, right? And then we gotta go back to our IR. Remember we had this debate. I don't know if it's an alkyne, a C triple bond C, or a C triple bond N, but now all I'm left with is a CN. That makes sense that that's the nitrile piece, right? So then we have another piece, our last piece then is CN. So now it's a matter of piecing these all together, right? We have this good chunk already done, right? This good chunk already done. Now we need to put this other stuff there. So how we have to put it? I think we have to put B right here, and then put this nitrile on the other end. That's the only way we can put it together. Do you see that last little bit, how to put it together? I'll draw it out. Silly O, not going away. I'll just draw it. So the N, we knew we had the O that's bonded to C, right? This was C and this is A. And we also finally knew B, right? B had to have no nearest neighbors. So this would be a CH2 that's a singlet, and it's around 3.45, so that's 2 things pulling on it. That makes sense. The nitrile will be electron withdrawing, and the ketone or ester here would be electron withdrawing. And this is at 4.26 next to the oxygen. This CH2 would be what kind of splitting? It would be a quartet, which what we had, right? And we also have a CH3, that's for the triplet, and we have that too. There you go. So let's count the hydrogens, right? Let's draw them in. Let's draw the hydrogens in even. There's 2 H's right here. There's 2 H's right here. Right, and let's label them. These 2 H's were B. These 2 H's were C. And these 2 H's were A, as we had marked above. So you always want to make sure you go back and check. Right? Did we cover our degrees on saturation? We need to have 3 degrees on saturation, right? Do we have 3 pi bonds or rings? Looks like we have 3 pi bonds, right? We have 1, 2, 3 pi bonds. We have 3 types of H's. I have only A, B, and C. That works. We didn't lose any elements. A would be split how? A would be turned into a triplet. Well, I have 3 H pieces of triplet. Good. C would be a quartet. That would be pretty D-shielded. It's next to an oxygen. So 4.26, 2H quartet. And they're the same coupling constant. These two are talking to each other. Good. B is at 3.45 next to a nitrile and this carbonyl. So it's going to be it's going to be D-shielded because of it. No nearest neighbors. Needs to be a singlet. Let's say we've counted for everything. Right. That last final check. This is a number 23 on a sapling question. The provided formula is C6H12O2. So let's figure out the degrees on saturation here. All right, so the DU, after calculating furiously, 1 degree of unsaturation. So of course means 1 ring or 1 pi bond. The other piece of information they give us, they say the IR, there's a peak at 1743. Look to your specific IR table. That should give you a clue. Well, you don't even need to. I mean, if it was a peak around 1700, what does that tell you? What kind of? It's a carbonyl. So C-double-bondo. So we know there's a C-double-bondo. And let's say we don't even bother with specifics. Right? Does that cover our Degree of unsaturation? Yeah, so we got our degree of unsaturation covered. So we have this CO piece, so let's subtract CO from our formula. So we have C5H12O. Right? Having looked at our NMR, I already got one functional group. Good. In our NMR, so this is a drawing, so I'll try to draw this as best I can. A little triplet. J is equal to 6.7 hertz. This is worth 2 H's, and this is at 4. There's another triplet, if that's 3, and that's 2. Just past 2, there's a, excuse me, that's not a triplet, it's a quartet, and that's worth also 2 H's, and its coupling constant is 7.6. So J equals 7.6. So those two protons are not talking to each other, right? They have different coupling constants. Not around, so this is 1 and that's 0. Around 1.5, it looks like we have a sextet. That's worth 2 H's. Right? And there's no coupling constants given for this one. Right, but when you see these sextets and these heptets and things like that, you know that they're getting split by 2 different types of protons, right? So that's that 2H must be in between a couple things, right? You should look at that and say, well, if it's split like this, that means it's getting split on 2 different sides by a different proton on each side, different type of proton on each side. All right, and there's 2 more big ones, 2 big triplets. Right at 1 or so. Each worth 3 H's. And they're both, the one's at 7.6 and this one's at 7.4. And what I would give you at this point, I mean, I would give you this information. They didn't. But we'll wait. We'll see if we can do it without it. All right, let's just do it without it. Okay, so what is this going to tell us? How many different types of hydrogens do we have? 1, 2, 3, 4, 5. Right? So 5 types of H. Let's label them. A, B, C, D, and E. Which 2 do we know for sure are next to each other? B and D. So let's just do those first, right? We know they're next to each other. Let's just do that first. They're easier to do with. So B, let's say this is B. B is how many hydrogens? 2, right? So let's draw B as a CH2. And we said D is coupled to it because it's the same coupling constant. D has how many hydrogens? 3. So let's circle these. So this was B, and these guys were D. Now, does the splitting make sense? B is a quartet, right? So how many nearest neighbors does a quartet have? 3. So 1, 2, 3. So that makes sense. And then D has how many nearest neighbors? It's a triplet, so it has how many nearest neighbors? 2. 1, 2. That works. Now let's look at the position, the frequency where these are at, and see if that helps us. So B here is at 2.1 or 2.2. Look at our tables. What's next to what's around 2.1 or 2.2? What would that be next to? Now don't forget, we've already narrowed it down. We have a CO, right? It might be next to that CO bond, right? Good. So let's just put that there. Right? We still don't know what's over here. But now let's subtract this new piece out. So we have a C2H5 piece. Let's subtract that out from our formula, C2H5. So C3H7O. So you have left over. Okay? Yep.
How did you know the single bond O goes next to B?
I knew that B was next to this because of this frequency, 2.1. So if you look on your table, right? When the hydrogens close to this carbonyl, it's around 2.1. So that's how I knew it had to be. And we already decided that we had a carbonyl. So it makes sense that B would be next to that if it's at 2.1.
It's, on the graph that, gave us, the 2.1 is next to,
It's-
a methyl with 3 H's, not 2.
It's about 2.5 to, so this is at 2.3, right? So the table says from 2.5, or 1.5 to 2.5, right?
Okay.
So that's right in that range, right?
So looking at the frequency helps you know what,
It's next to, right? So the frequency tells us, right, whether it's shielded or de-shielded, right? What it's next to. So we really got to use this in conjunction, right? To decide, well, B is next to this because this is at 2.1, and that falls right in that range where, right, H's that are this close to the carbonyl are, right? So what do we can check off? We can check off B, and we can check off D. Now for these other ones, right, 6.7 and 7.4, right, the coupling constant here, those aren't the same. But then we look at C here, and C is all split up. It's all split up. Uh-huh. Yeah. Right? So it makes sense that I'm going to guess that A is getting split by C, and E is also getting split by C. That maybe E and A are surrounding C, right? Because C is all split up. These guys aren't talking to each other. But they got to be talking to somebody because they're split. Who's left over for them to talk to? It's got to be C, right? So let's put C, which is worth 2 hydrogens. Let's put C right in the middle. And on one side, it's bonded to a CH3, which is E. And on the other side, it's bonded to A, which is CH2, right? So label these, right? So we knew, well, we didn't know for sure, but we think this is C because we know A and E aren't talking to each other because they have different coupling constants. So we assume, because C is all split up, that C is talking to both of them. So C would be in the middle of them. E would be on the end, right? Because in this situation, E is a triplet. How many nearest neighbors does E have right now as I've drawn it? 2, so it would be a triplet. And if I draw this one as A, how many nearest neighbors does A have in this situation? 2, so A would be A, and A is a triplet. Good. So let's subtract out this piece. C1, 2, 3. So minus C3, H7. All we're left with is the oxygen. Okay? Well, let's take a step back and look back at, right? A has to be bonded to something. Or the carbon that A is on has to be bonded to something. And A is way down here at 4. What do you think A is bonded to? Oxygen. Right, but I don't know where that's at. Well, now I have 2 pieces. So the answer, right, that means this oxygen and this carbon have to be bonded together, right? That's the only thing that's left for it to work. It has to be bonded together. Yep.
I was following you up until that CO.
What's the frequency for A?
Is about 4.
About 4. So that's shielded or de-shielded. And we have an oxygen left over.
Okay.
Let's put the oxygen bonded to it. So now I only have 2 pieces, right?
Yes.
So they have to go together. Right? There's no other way to put them together. They have to be right next to each other. Right? So the final answer then is that. I'll draw the H's in. Right? Because now we're going to go back and double check. Right? We always want to go back and double check our answers. So these 3 will be split how? What kind of splitting would those 3 have?
Triplet.
Triplet. And we called that one D. These 2 H's are around 2.1 because they're right next to the carbonyl, right, as our table shows. What were those ones? The B, they'd be a quartet. These two H's are right next to the oxygen. They have two nearest neighbors. Two nearest neighbors you split into a triplet. So you call these A. These two were all split up, right? Bunch of different nearest neighbors. Call that C. So it has a triplet of quartets, perhaps, for the C, or a sextet sometimes. And then finally, you have E, right, which has two nearest neighbors, so it's a triplet. So what we could have put in here, right? So what kind of coupling constants did C actually have? What were the two coupling constants C have? What were they? 6.7 and 7.4. Right? So C actually has two coupling constants. They just didn't give them to you because you should have looked at this and said, well, A and E aren't splitting each other, so they must both be talking to C. So C has 6.7 and 7.4. Those two coupling constants.
You know how like they're like A and C, A and E, I mean, are both triplets, and then like C looks like it's like
Split up by a bunch of stuff.
6.
Yeah.
Or 6.
Well, you know it's split by a lot of things, so it had to be next to two different things. That's kind of the idea. Yep. Good. We covered our degrees on saturation 1, right? That looks good. I say we're covered. So another sampling problem. This is number 22. It's a C6, H3, 5, 7, 8, 9, 10, H10, O2. God, I'm in H10, O2. So let's do degrees on saturation. What do we got? Right, degrees on saturation tell us 2. So 2 pi bonds are rings. Some of the other information they give us is the IR. It says from, 3,000 to 3,580, a big old broad peak. That tells me OH of some sort, right? And then a peak at 1698, and another peak at 981. Now, if you see those ones around 981 and 800, you should be pulling out your table, right? Pulling out your table at the IR table, the specific alkene stretches. So 1698, that tells us what? What kind of peak? What kind of functional group? What kind of functional group is C del bando? So there's probably a C del bando somewhere. And 981 should be real specific to a stretch on your sheet. That's 9. Yeah, 981. What does it say in your table?
For trans,
Yeah, 980.
980 to 960.
Yeah, so this is pretty close, right? So this, from our IR, is telling us there's a trans alkene involved here somewhere. Don't know what on the other ends, but so the IR here gave us a lot of information. There's also this UV. There's a UV spectrum at 212, and we hit on this, right? UV at 212 nanometers. I think I gave you the example of a ketone is that by itself was at 190 something. So 212 means, right, if you have a UV vis, usually that means you have pi bonds. And I would even go so far as to say you have conjugated pi bonds, right? So you have the pi bonds are lined up together, right? Pi bonds conjugated. Right?
How would you know that?
Just because it has a UV vis spectrum, right? Because UV really, right, it's all about the pi bonds, right? Pi to pi star. So if you have a UV spectrum, that usually means you have, for sure it means you have pi bonds. And a lot of times they wouldn't give it to you unless those pi bonds were conjugated, right? So it means those pi bonds are probably next to each other.
You know how like the UV, like the spectrum is like 200 nanometers to 400?
Mm-hmm.
Do we ever see anything like?
The more pi bonds we have, the longer the wavelength we'll get, right? Remember that whole discussion? So don't forget the UV vis, right? So this doesn't mean, right, we only have 2 degrees on saturation. And so we don't have that many pi bonds to be conjugated, but if we want to make these pi bonds conjugated, what we have right now, what do we have? We have a CO, C del bond O, and a pi bond here, right? So we just go ahead and put them together, right? Yeah. Sure. So we know the alkene is trans. We still don't know what's up here. And we don't know what's over here. And we think we have an OH. So that IR and UV vis just gave us a lot of information, right? So if you were carefully analyzing it, right, remember that's what I said, that table on your IR table about the alkenes, it really gives you lots of information. It tells you if it's cis or trans or terminal, right? The NMR is going to tell us that too, but this is a pretty good start already. So let's subtract out what we have. So how many carbons do we use? 1, 2, 3 carbons. C3. How many H's? Just 2 H's, right? And 1 O. So it's C3H8O. But we have an OH too, right? So let's subtract our OH out of there. So all we're left now is C2H7, right? Is that right? Gosh. What does it say? C2 will not work. C3H7. There we go. We haven't even looked at the NMR yet. We've already got more than half this molecule done. Right? Okay, so what does the NMR show? Okay, this is going to be a little tougher to draw. So there's a peak at some sort of weird looking peak like this. That's worth 1H. This is around 7. We got another peak. This is around 6. This is worth 1H. This has 2 coupling constants, 15.6 and 7.0. So 2 coupling constants there. This one has a coupling constant of 15.6 and then a little guy of 1.6. Then you have to humor me here. There's gonna be a gap. We're gonna go down to around 2 now. And at 2, there is a doublet of quartets. So imagine what that looks like. All right, a doublet of quartets. This bad boy's got, oh gosh, it's got 2 H's, and it has 7.4, 1.6, and 7.0 for coupling constants. So it's got 3. So it's coupled to 3 different things. That's interesting. I'm going to have to skip down here. I'm running out of room. Go down to here, and we have another one around, this is now like 1.5. And I have a, yep. Another one's worth 2 H's. That's at 7.4. And then finally, thank God, down here at 1, I just simply have a triplet. And this guy is worth 3 H's. And its coupling constant is 7.4. Woo! All right. So how many types of hydrogens do we have? 5. So 5 types. Yay. Let's label them. A, B, C, D, and E. All right. So we already have, let's not worry about the really weird ones around like A and B. Those there's some funky stuff going on over there. And plus those are down, they're probably my alkene protons, right? These 2 guys are de-shielded, like quite a bit actually. But we know they can't be aromatic protons because we don't have an aromatic ring. We've already used our 2 degrees on saturation. So these H's right here that I'm circling, that are on the alkene, are probably these H's, A and B. I don't know which one's which yet though. That's the hard part. I don't know which one's which. Right? Don't know which one's which. Okay? But I know they're coupled to each other, right? and the coupling constant here is 15.6. So you should remember, there's two coupling constants that we wanted you to remember. 15 and 10. If the coupling constant is 15, what does that tell you? What kind of alkene is it? Trans. If it was 10, it's a cis alkene. Right, so the IR told us this too, right? The IR also told us, this 981 told us it was trans. But the NMR also told us the same thing, reconfirming that. Good. So just to clarify again, right, these numbers, right, this is how many H's is worth, 1H, 1H, 2H, 2H, 3H. These numbers are the coupling constants. So this tells us how they're being split, who they're talking to, right? So this has 2, this has 2, this has 1, 2, 3, 2, and 2. Right? So the easiest one first, right? Let's just make it easier for ourselves, right? Looks like D and E are talking to each other. They just have one coupling constant each. Let's just do those two together, right? So E, let's say, is a CH3, and it's next to D. Right? So we say there's 2. This is E. This is D. I don't know what D is coupled. Well, no, that's not true. I do know what D is coupled to. Who's D coupled to? It's coupled to E. And anything else? And C. So it looks like D and C are also talking to each other. C is worth 2 H's. This is C. Right? So now it also, though, wait a second now.
Why is C talking to?
Now C is talking to 3 people.
C and E.
Yeah, so now what is going on with C? So let's just first so we're down to nothing, right? We got our last piece, don't we? So C here, this piece right here is our C3H7, so that covers this now. So we have 3 pieces left, and we got to put them together. There's only actually one way we can do this, right? Because C has to talk to which one? C is talking to both B and A. And we said both of these guys one of them's B and one's A, right? So where do I have to put C? Can I put C over here? Or do I have to put C over here? I have to put it up here.
Yeah,
So you don't need to know which one's A and which one's B, do you? You really don't need to know.
so you have the OH to.
So where's the OH have to go then?
the bottom.
Right there. So it looks really complicated, but at the end of the day, C just needs to be close to A or B, whichever which ones these are. And I know this one's A. You wouldn't be asked to know this one's B. You don't need to know that. And so overall, the whole thing, or if I move this up, what it looks like then, OH, because the other peak, I didn't mention this, would have been helpful. There was another peak, so it wasn't just 5 types. There was also a broad singlet, like a fat little singlet, at around 11.9. That's where the OH and carboxylic acids are at, right? So that could have made this really easy for us, right? There was another peak down here. I didn't draw it in. There's another peak down here at 11.9. If you look at your table, at 11.9, it's usually the H from carboxylic acid or even the aldehyde. So we would have known that was also carboxylic acid then from the NMR. Make sense?